Yeah, I'm very happy to be here, and thank you all for coming to my talk today. We'll be talking about neural algorithmic reasoning, which is one of, in my opinion, most exciting emerging areas of representation learning today. And arguably, I think it should come into contact with a lot of the interests of the people in this room. So hopefully we'll have a nice, interesting discussion today. As mentioned, my name is Petar Veličković. I'm a staff research scientist at Google DeepMind and an affiliated lecturer at the University of Cambridge. And what I'm going to be talking to you about today, just to kind of set the stage and put you in the right frame of mind, we're going to be talking about classical computation. That's going to be, I guess, the centerpiece of the talk today. And when I say classical computation, I mean the kinds of things you might typically encounter in an undergraduate course on algorithms and data structures. So think things like sorting, searching, pathfinding, interesting ways to organize data so that you can more efficiently retrieve it, and so on and so forth. However, because this is a deep learning oriented seminar, we will also be talking about how can we take that classical computation and capture it inside neural networks. So that's going to be kind of the main theme of what we'll be talking about today. And I feel like it might be useful to first address the question of why should we even bother about doing this? Like, why should we care about trying to capture classical computation with neural networks? Because you can think of them as sort of classical computation is good for one thing, neural networks are good for another thing, and we can just leave it at that. But if you look at the kinds of properties that classical computation has, which neural networks don't have, you can enumerate things like you're able to prove that the computation will terminate correctly in a certain amount of time with some usage of memory. It will typically strongly generalize. So you might design an algorithm by looking at a few instances on the whiteboard, but this algorithm will then work even if the instances are much bigger. And also because of the way you write down the algorithm, you can usually interpret what it's doing and also compose it with other algorithms. So when you look at all of these properties, these are exactly the properties that neural networks tend to be really bad at and are arguably the main things we need to improve them in. So arguably, there is some benefits to bringing these two worlds closer together. And I would argue actually these kinds of properties, provable correctness, strong generalization, robustness, interpretability, those are critical if you want to make AI useful and instructive for humans, right? So for example, imagine you want to make an AI system that will teach someone about concepts in math. That system should ideally not give wildly different answers depending on whether you pretend you're being judged by an expert in your prompt, right? Ideally, if it truly understands the concept, it should be invariant to those kinds of stimuli. And as long as that's not the case, this is not a system I would very happily put into a position where it can teach humans about something. And arguably, these kinds of robustness properties are a key missing step to building generally intelligent agents. Because if you want to truly have an AI scientist that can adapt to brand new situations, it needs to be able to reason about how do those situations differ from what it has seen before. And arguably, that's also out of reach of the systems today. So, at least in my opinion, I hope you agree with me, our best state-of-the-art scaled AI systems are quite poor at all of these things right now. So it might be a good idea to try to make them better. And I won't have a lot of time in this talk to talk about models specifically. Like I'll try to talk more about ideas and the way we achieve those ideas. But I feel like one important point to mention here is what is the rough class of models we're going to be talking about in terms of which neural networks we're going to use to capture computation. And specifically, the key player here is the graph neural network, or GNN. And there is not much I can say about GNNs in this talk other than they operate by taking a local neighborhood of a particular node in a graph. So imagine you have a graph with features in every single node. A graph neural network is just a local function f, which operates over all of the features in that neighborhood and updates the features to some latent state. Then you can stack a bunch of these layers together, apply them to every neighborhood in parallel, and that's how you get your graph neural network. As long as this function f is what we call permutation invariant, meaning it doesn't matter in what order I ship the neighbors into this function, then this will be a well-defined graph neural network. And you might also be interested, how do I actually implement this local function? Well, a very popular blueprint, which is a remarkably general framework, is this message passing paradigm, where basically so now if you see here, I've zoomed in from the previous picture, I've zoomed in to node B and its neighbors. So what happens is along every edge of the graph, you compute a message vector using this function psi over here. Oh, interesting. I didn't realize that would show. I thought So basically, this psi function here computes the message function, which computes this message vector to be sent across the edge. And then you take all of the message vectors and you combine them together using this aggregation function O+. As long as that function doesn't depend on the order of the operands, you're good. So you can imagine this O+ being something like sum, max, average, whatever works, right? And then once you've aggregated all of your messages in your mailbox, you can then further process them using this update function phi. And we also have this nice skip connection where xi is given as an extra input to phi just to avoid getting that information lost in the neighborhood. So as long as you design this O+ to be permutation invariant, this is a valid way to implement a graph neural network. And arguably, it's a very general way to build discrete deep learning in general. In fact, you can show that most deep learning discrete architectures can be very easily written down using this function. Among other things, transformers are a very special case of this equation. Now, as I said, I'm not really able to talk to you more about GNNs in this talk, mainly because I have a limited amount of time and I need to talk about some more algorithmic topics. But GNNs are a topic that's very close to my heart. It's something I've done my PhD in. I've taught about it extensively. And there's lots of material you can find online if you're interested to hear more about GNNs from me, including this talk over here, which has up until now accumulated about 70,000 views on YouTube. So I would say it's fairly robust as a starting point of how to implement these models in more details. So that aside, let's talk about capturing computation. So our study will start from some question that might seem interesting at first, but not necessarily very consequential, which is, can we take these graph neural networks and teach them to execute the steps of classical algorithms? So what do I mean by this is, imagine you have an input to some algorithmic task like breadth first search or something. So you want to find shortest paths in an unweighted graph. You have an input which specifies the source vertex and the graph structure. Then you have some encoder function which will embed these features into some latent state. Can I then learn a graph neural network over this graph such that I can predict at the output stage what the correct shortest paths in this graph are, and maybe also what are the distances from the source node, right? This is the question that we are trying to answer here. And you might say why this might make sense, because if a neural net can take the inputs and produce the outputs in a way that is robust, arguably it has indeed captured the computation. So it's a good place to start. But also it's a really cool way to benchmark how powerful these neural networks actually are in a very nice controlled setting, which you rarely see anywhere else in deep learning. Because if you're learning to simulate an existing algorithm, you have infinite data. You can generate inputs of any size you want, as long as they conform to the preconditions. The algorithms themselves feature very complex data manipulation. So you're not teaching your model some trivial benchmark. It needs to learn a generalizable rule with lots of branching, loops, and whatever. And lastly, because you have a very clearly specified generating function, you can even do rigorous explainability and credit assignment. Like you can actually check, has the model learned what it needs to learn, or has it just picked up on stupid biases in the training data, right? And this maybe invites a more generic question, which is, what is it that makes a neural network better or worse at fitting certain algorithmic tasks? This is a general question that we would really much like to answer. And one thing that you might find surprising if you're not familiar with the literature is that actually we can rigorously prove stuff relating to this question. Specifically, the key concept that will allow us to talk about this is a notion of algorithmic alignment. And once again, I won't have enough time to go into details of the definition of algorithmic alignment, but I think it's something that can be very nicely explained pictorially. So you say that an algorithm is aligned to the computations of your neural network, or vice versa, that your neural network is aligned to some computation. If I can break down the equation that the model is implementing and line up the parts of it with the parts of what the algorithm is doing. So here on the left-hand side, we have Bellman-Ford, which is one of the most standard dynamic programming pathfinding algorithms. On the right-hand side, we have the GNN equation, just as I showed it to you before. And you can see you can very neatly map the different parts of the message passing equation to the dynamic programming equation. So the distances to every single vertex can be seen as node features. The act of adding the edge weight to these node features can be seen as computing the message function. And the act of minimizing over all of the neighbors can be seen as the aggregation function O+. So this is what we mean roughly by algorithmic alignment. We can break up our neural net into parts, those parts line up with the algorithm. And you might see me using the word alignment quite a bit. This is actually a bit in contrast with the way alignment is typically used nowadays in language models. It's alignment to human preferences, but arguably alignment to human preferences is very weird. You're aligning to whatever the human will give a thumbs up to, which may or may not actually make sense. And it might encourage the network to hallucinate, especially on reasoning tasks. Whereas here we have a very rigid, well-defined computation we're aligning ourselves to, so we can be a lot more rigorous about what does it even mean to be aligned. Arguably, we have a greater chance of success here. So if you subscribe to this notion of algorithmic alignment and you go away and define it, you can actually mathematically formalize why an architecture might be better for a task, algorithmic execution task. And when I say better, I mean in terms of sample complexity. You'll need fewer training instances to learn to execute the algorithm up to error epsilon, right? That's generally what we mean by better. And this first theorems have been proven in this seminal paper from MIT, What Can Neural Networks Reason About? I highly recommend reading it if you're interested in any of what I talk about today. And in this paper, they prove a theorem that says better algorithmic alignment means better generalization. And specifically, why do we care so much about GNNs here? They also make a very important observation that these GNN neural networks algorithmically align to the broad class of dynamic programming algorithms. And I hope it can sort of make sense why that is the case, because you can interpret your node features as basically the subproblems that you're trying to aggregate together. And the message function is kind of giving you the scores of each subproblem. And then the aggregator picks what is the subproblem to choose when it's recombining the solution, right? And this is in the case of Bellman-Ford, every single node is a subproblem, right? You're computing the distance to every single node, and then you can recombine those distances at every single step of the way. So this is generally the reason why we care about GNNs so much in this particular domain. And now I'll tell you a little bit about our own first excursion into the area, neural execution of graph algorithms, which was, oh, is there a question?
Actually, I wanted to ask about this. This algorithmic alignment that you are mentioning, that's limited by the structure of the graph neural network. So graph neural network can only represent certain decomposable structures that you showed, like this problem, right?
Yeah.
So in general, we need to think about other graph neural networks, or is it?
Yeah, so yeah, we'll talk a little bit about this. Actually, the point of our paper, which I'm going to show next, shows that this idea doesn't allow you to be reckless, and you need to carefully line up for different algorithms, different types of GNNs. In fact, in the original paper, they also look at an MP hard problem like subset sums, where you need to reason over all possible bit masks of your input. And there they say GNNs are not good enough. We need to have, at least unless P equals MP, which is unlikely to be true, we need to have a structure that like picks every single subset of your sequence and then does a RNN on every single one of those and then aggregates, right? So that algorithmically aligns better with like subset sum dynamic programming. So just to be clear, this is a very good observation, but hopefully one that we will revisit just now. So in this paper, which actually appeared concurrently with the algorithmic alignment paper at iClear 2020, we made our first steps in trying to understand how to build models that are better aligned to algorithms, but from a more empirical point of view, because let's reconsider what we really care about here. Algorithmic alignment is indeed a very powerful tool. It explains why a GNN is a better choice than, for example, a deep set or an MLP architecture, but it doesn't allow you to be reckless, strictly speaking, because even though GNNs might be the right class of model for dynamic programming backed algorithmic tasks, you cannot just throw any GNN that's expressive at the problem and expect great results, especially out of distribution. And arguably out of distribution, so generalization on inputs outside of your training set, is arguably critical for a reasoning system. Like a reasoning system should not fall apart just because you gave it a 2 times bigger input or something like that. So if your model truly learned to behave like an algorithm, it should work across a wide variety of inputs, not just the ones captured by the training data. And if you're not careful, you throw your basic expressive GNN at this problem, it can very easily overfit to some specifics in the input distribution for your training set, and therefore sidestepping the actual algorithm it's supposed to learn to execute. And in our paper, we make several key observations on what tiny changes you can make to the GNN architecture to make it better aligned with pathfinding algorithms. And as a result, we are able to generalize to graphs that are 5 times bigger at test time, which the previous paper, the algorithmic alignment paper, wasn't able to do because they just threw your usual expressive GNN at pathfinding problems. And actually, I think not only are they not able to generalize to bigger graphs, I think they end up with NANs or some other exploding gradient issues. So what are the three key insights that we had in this paper? The first one, it might feel obvious now, but at the time it was a little bit more out there, is the algorithmic alignment paper used a GNN that was basically just a fixed stack of layers, which meant you are limited in how much compute you can do. But for most algorithms, especially as inputs grow, the complexity also grows, and you need to basically account for more steps that need to take place to solve for that particular input. But with a fixed layer unshared architecture, you're unable to do this. And in fact, this is another limitation of modern day transformers, because you have a fixed number of transformer blocks. So at some point, it's going to run out of computational complexity and it's going to start hallucinating. You ask it to multiply large enough numbers, at least without explicit tool use, it is going to struggle and it's going to pretend it knows the answer, right? So same problem with the GNNs. How can we make it work and make it iterate for more steps at test time? Well, the only solution we can really do here is to have a shared processor network in the middle, right? So now we have one GNN layer, which is shared, and we iterate it for however many steps we want at training time or test time, and those numbers can be different, right? And this is also nice because it aligns with the encode-process-decode paradigm, and it encodes for the fact that really what you're trying to learn is a rule that gets repeatedly applied to your input, right? So this is also very nice for any iterative computation, any while loop or anything like this. The second thing, which also, you know, if you're not familiar with GNN literature over the past years, this might feel like a very trivial thing, but we actually had to fight against lots of folklore when proposing this. You know, that aggregation function you use over there, the O+, you know, you look at what Bellman-Ford and many other pathfinding algorithms are doing, really this should be a max or a min, right? Because it lines up with what the aggregation is being used, and it lines up with like selection of neighbors. However, I must stress this was a very controversial decision at the time because there existed previous papers on how powerful GNNs are that clearly said that max GNNs are strictly weaker in terms of isomorphism classes of graphs they can distinguish compared to sum or average, right? So using max was seen as very controversial, but the point of the matter here is I don't care if certain, you know, non-isomorphic graphs get mapped to the same value if those non-isomorphic graphs have the same shortest paths. Like I don't care about that, right? So here the usage of max is actually a good idea, and actually contrary to the folklore, we now have actually solid theoretical evidence why choosing that aggregator is a good idea. The third insight, which also tries to expand a bit on how we typically train supervised learning machine learning models, is rather than go straight from input to output, we can often make advantage of algorithmic invariants. So you can reason about what will be the state of an algorithm after a certain number of steps. You can supervise your model explicitly to follow that. So for example, in a pathfinding algorithm like Bellman-Ford, after k hops, you would expect to be able to compute all of the shortest paths that use no more than k steps away from your source node. And in a similar manner, you can supervise your GNN after k steps to predict those k hop shortest paths. And this now allows the model to be instructed to follow the computation more closely. And it has helped us a lot in this initial paper to achieve better results. Now, you can actually keep playing this game. So our first paper showed that you can do these three things to align better with iterative computation. But really, this is just one paper in a sea of papers trying to do the same thing in different ways. So you have shuffle exchange nets that align with sequence and log n algorithms using routing networks. You have iter-GNNs that align with homogeneous iterative algorithms using various termination models. You have our very own PGN, which aligns to pointer-based data structures like link cut trees and disjoint set unions. You have persistent message passing, which aligns with structures with auxiliary memory. And actually, as you line up all of these different game-playing architectures, which subtly change a GNN to be better aligned with certain classes of computation, the general message that seems to arise from this is that fine-grained aligned architectures are a better idea if you want to generalize out of distribution. And this eventually led us to have better fine-grained theory that explains why this is the case. Actually, the results from our paper inspired the authors of the original algorithmic alignment paper to publish a follow-up next year, linear algorithmic alignment, which explains why our usage of max helped the model generalize much more than using sum. And this is a result I'm happy to discuss afterwards if you're interested. Then further, this result was further generalized by the group at Purdue, which showed that actually the idea of linear algorithmic alignment is just a special case of a more general causality framework. So to truly generalize, you need to have some causal model of what your data looks like at test time. And then further, in my collaboration with Andrew Dudzik, we were able to show that if you want to talk about rigorously what does it mean for a network to be invariant to a step of an algorithm in some sense, you need to talk about, you need to bring in category theory tools. It's basically not possible to do with weaker mathematical tools. And we have a paper at NeurIPS that talks about this alignment. So this was roughly the state of play around the year 2022. And as I said, the talk is about the melting pot of NAR. I'm going to present some of the newer stuff we were involved in. And actually, just at one ICML workshop 1 week ago, we have presented 4 papers that try to push the envelope both in terms of game playing and theory. So I'll give you first a quick rundown of these papers, and you can look them up on the archive for some specific details. But hopefully you understand enough about what it means to play the game that I can very easily explain these to you. So first, the 2 architectural novelties, the recursive algorithmic reasoning and neural priority queues, try to add additional computations into the GNN equation such that it aligns better with certain classes of algorithms. And you can basically tell from the titles, right? The first one tries to make graph neural networks better at recursive reasoning. Arguably, recursive algorithms are a big problem for any neural network. How do you make a network better at doing recursive reasoning? Well, you endow it with a stack, right? So every single step of the way, you have a network that predicts a 3-way outcome. Either you push your current embeddings onto the stack, which is like a recursive call, or you do a pop from the top of the stack, which is equivalent to context switching and going back to whatever was at the top of the context, or a no-op, which means you're just executing your current stack frame and you're not changing anything. So based on this structure, with a bit of auxiliary supervision, together with my co-authors, we have been able to get really good performance on executing recursive algorithms. In neural priority queues, as you might expect, we are trying to do better on algorithms that require a priority queue data structure. And what we do basically is we make a differentiable soft version of push and pop instructions, which you can kind of see schematically here. It's basically a mixture of self-attention with very clever arithmetic to manage how much of each item you've attended to, so that if you've attended too much to an item, it actually gets deleted from the queue, right? Which is kind of equivalent to popping out one item from the queue. And using this, we have been able to get much better, strong generalization performance on algorithms like Dijkstra and Prim, which rely on priority queues, but also many other algorithms that rely on that would rely on some kind of persistent memory to get their performance better. So a common theme in both of these really is that you have a stack or you have a queue and you're pushing a state from a certain point in time, but that state doesn't change afterwards. You can access it exactly how it was. This is a big difference to how we typically build both GNNs and transformers today, right? Because you have like these different nodes or token embeddings, and they update all at once everywhere at every step, but no real, self-respecting algorithm, unless it's embarrassingly parallel, can afford to update every single state, every single variable, every single time, right? You have to update a few of your variables, then use that result to update some others and so on. So allowing to give a GNN access to persistent memory allows it to basically have a rigorous access to this identity function, like just a stored value that it computed sometime in the past, without need to kind of worry about preserving it over many steps of updates. And this, in my opinion, is the key reason why these architectures are performing better. And therefore, I think these are ideas that might be able to work even beyond the realm of algorithmic execution. And I think some of these have already been tried in one way or another in language modeling. The theoretical papers also, start from this idea of, your actual algorithms don't update all the state all at once. They update some variables, then they update some other variables and so on. So you cannot expect a GNN, which is a fully synchronous model, to easily be able to deal with this. And in the 2 papers, parallel algorithmic alignment and asynchronous algorithmic alignment, we try to tackle this problem from 2 directions. In parallel algorithmic alignment, we just say, try to make your target algorithm as parallel as possible. It's basically perhaps a slightly silly observation in retrospect, but we have been able to prove that if your algorithm updates more state at the same time, it'll have more efficiency with respect to the GNN, and the GNN empirically will fit that algorithm a lot better. And with asynchronous alignment, we actually realize, okay, the true general purpose algorithms we might want our models to be able to execute in general are asynchronous. You cannot really afford to update all the state all at once everywhere. It's just not that parallelizable. But we also acknowledge that you cannot really build asynchronous GNNs on today's hardware in a way that scales, right? So GPUs and TPUs, they are designed to build models that update everything everywhere all at once. So what we try to do then is like, okay, we will implement a synchronous GNN, but let's mathematically constrain it, like find mathematical constraints on the message function or the update function, such that it doesn't matter if it's synchronous or asynchronous, like such that I can probably get the same result, even if I mix my messages all over the place from different layers and something like that. So with the right form of constraints on phi and psi functions, we can actually get full asynchrony. Specifically, what you need is idempotence of the aggregator, associativity of the update with the aggregator, and you need your psi function to be what is known as a monoid homomorphism. I don't have enough time to go into the details of this, but happy to discuss it later if you're interested. Okay, so that's the first part of the melting pot. Some interesting game that we can play about mapping graph neural networks to classical computation so we can better capture it. And also some additional theoretical work we have done on trying to explain better how to build architectures that are better at capturing said computation. But one thing that I haven't told you yet is why bother with all of this? Like, what can we do once we have trained the model to fit the classical computation? What can we do with it afterwards? And that is where neural algorithmic reasoning comes into play. With Charles Blundell, I have described this in a position paper that we published in 2021. I will give you a quick rundown of what the blueprint is about, and then we will dive into some more melting pot papers that try to show how this blueprint works in practice. So, in order to ground why this pre-training can be useful beyond just benchmarking utility of execution utility of various architectures, let me prime you with a simple example. Find me the optimal path from A to B, right? Now, if you come from a background similar to mine, I've done my undergrad in theoretical computer science, and I imagine at least some of you share a similar background. When you read a question like this, you will interpret it in a very singular way. And actually, when I prompted language models like BARD or ChatGPT this exact same question, they also took it in a very singular way. You will assume that this question means I'm giving you a weighted graph and I'm asking you to find shortest paths in this graph. So you will proceed to take out your Dijkstra hammer and apply it to this problem and get your shortest paths, right? But there is nothing about this question that said, I want shortest paths. It just says, I want optimal paths. And there's nothing about the question that says, I'm giving you a graph like this, right? And I have personally experienced this misalignment when I tried to put GNNs inside Google Maps, okay, to predict travel times of different agents in traffic. And this is now a system that's deployed everywhere. So even in Montreal, you take out your phone, you ask, I want to go from A to B. Your phone says how much time it will take. The travel time you get as an estimate is served by a graph neural network that we have developed at DeepMind together with our partners at Google Maps. But the data we got to play with there was not like this, right? The data we got were phones inside people's cars, and those phones move with the car. And based on that, you have to estimate how quickly the traffic is moving, whether or not there's various rush hour conditions, weather conditions, traffic lights, roadblocks, and whatever, all sorts of dynamic things that make this graph really challenging to even figure out what it is in a meaningful way. Because this, to be able to apply a pathfinding algorithm, you need one scalar in every edge. I don't think it's very easy to summarize the wealth of this raw data into these scalars. And actually, this data can even be adversarial. I don't know, I hope some of you have seen this famous example of a guy who walked down the street in Belgium and he put like 100 phones in his sack and he walked down the street. And in the process, convinced Google Maps to route all traffic away from that street because it thought it was very slow traffic by the movement of the phones. So just to say, it's really tricky. And traditionally, how do we bridge this gap? How do we bridge the gap from the real world complexities to something where an algorithm is applicable? Well, typically it's done by us, by humans, right? By experts who figure out either manually how to map the data or write some heuristic code to map the raw data into something that the algorithm will expect. And this naturally raises the question of, can we ever hope to manually do this? And you know, I think we've known as a field for a long time that the answer is probably no. I think some of the earliest papers on this were in the 50s. But to be fair, theoretical computer science doesn't concern itself always with bridging this gap because we're working in this nice, isolated, abstract world where everything is nicely specified and we're just trying to prove stuff about the abstract problem. So crossing the divide might not be that much of an issue for a computer scientist. But arguably, it is a divide between algorithms and the real world problem you're supposed to use them to solve. And if you want to satisfy the strict preconditions of an algorithm, it might mean you're going to drastically lose information. Or put very bluntly, it doesn't matter if your algorithm is provably correct if you're executing it on the wrong data. It's as simple as that, right? Garbage in, garbage out. And that's tricky even without talking about issues like partially observable data. Like you might not have enough data to completely accurately map to the inputs of an algorithm. You might need to guess sometimes. Yes.
Yeah. So about like in your previous slide with like the graph, right? You're saying like, oh, like it's difficult to summarize everything in like weights or graph, etc. But like maybe it's possible, it's just like hard to learn exactly what those weights are, but maybe like there's like a good choice of weights that matches well with like maybe there's a good choice of weights such that people's preferences in terms of path match well with like the shortest path, the shortest weighted path on that graph. It's just like it's hard to learn what those weights are, right?
Yes. So, okay, I'm not debating here, and these papers do not debate whether such weights exist. The debate is whether humans can find them easily. Sure. And the argument is they cannot. And actually, you mentioned nicely human preferences. The problem is preferences also depend on who you ask. So Google, for example, might not only be interested in routing everyone on the greedy route, which might clog the main artery of the traffic, but also we might care about pollution, right? So we might want to even recommend someone to take a slower route on a bike or something if they are okay with that, even though it's not optimal in the shortest sense, right? So the notion of optimal really varies depending on what you're optimizing for and whether it's local or global. And it's a lot of considerations that are not easy to factor in.
Like arguably the weights should vary according to place.
I mean, yes, in principle, yes, but I don't see how we, without the use of some learning system or a customized executor, are going to be able to do this. So this is really the argument I'm making. Yes, I mean, what I'm going to propose next is basically injecting these algorithms inside the learning system. So that's kind of trying to do what you just said. So yeah, put differently, I will show you one way in which you can attack this core problem by what I like to call neuralizing the algorithm. So taking the computation and wrapping it inside the neural network in some way. Now, what do I mean by neuralizing? It's actually a very simple extension of what I showed you before. If you remember this picture, I showed you we can train a GNN that's algorithmically aligned, at least in principle, by sampling lots of inputs for the algorithm we care about, and then teaching a model to execute it. Like there's this encoder function mapping it to a latent space of a GNN. You then spin your GNN processor for a certain number of steps. Then you predict the output based on a decoder network, right? Now, once you have this GNN, this high dimensional to high dimensional mapping is in some sense, hopefully capturing the computation. And it is basically a component that you can plug into a neural network without a lot of effort. So that's basically what we suggest you do. So you take your real world problem with your raw data, you learn new encoders and decoders that go to and from your processor network. And in this way, you are basically applying your abstract algorithm in a high dimensional space over the inputs you care about without having to go down this tricky path of first going up and then running the algorithm, because this path of going up is a bottleneck that's tricky for humans to do. So this is one possible way in which you can circumvent this. And in a different way, you're pre-training a GNN, or this doesn't even have to be a GNN, by the way. This can be a scaled up, differentiable, distributed version of an algorithm as well. We're completely open-minded about this. But what we've seen a lot of success with so far is take a GNN and pre-train it in an algorithm, and then deploy that GNN on the natural task you care about in such a way you're able to run a classical algorithm on inputs that were previously considered inaccessible to them. And I must stress, this is not just something that we're proposing. We have lots of proofs of concept of this idea working. I believe one of them was presented in this group a few weeks ago, the Excel paper. But what I will actually show you here is a brand new one. So kind of going back to the melting pot, we are trying to show you some of the latest papers that we've published in this. And we actually recently have an iClear spotlight on dual algorithmic reasoning, which is our most scaled up version of this system to date. So what have we done in dual algorithmic reasoning? We are interested in taking all of the blood vessels of the mouse brain and classify those blood vessels for, are they veins, arteries, capillaries, and these sorts of things, right? Now, I am no expert in mouse anatomy, right? Like, I have no way of saying what is the meaning behind what blood vessel has which function. However, I do sort of understand that the purpose of the blood vessel is to conduct blood flow. So if I have some way of analyzing the flow properties of this network, that might be very useful in classifying what blood vessel I'm looking at. So this is a very nice target for our blueprint, right? We teach a graph neural network to execute two standard algorithms on a flow network that are actually duals of each other, max flow and min cut. This is the reason why we call it dual algorithmic reasoning. And in fact, learning both of those simultaneously is critical to the success of the method. You cannot just learn one or the other and expect good results. We got the best results when we learned on both of them simultaneously. And once you have that GNN, you hook it up to another GNN that's processing the blood vessel graph, and then you use it to predict the segmentation of the brain, right? This is what we've done. And why do I mention that this is our most scaled up NAR yet? Well, because we typically train these models on relatively small algorithmic inputs, like 16 to 32 nodes, mainly because you need to fit over a very long trajectory of execution. So very quickly, you'll run out of memory if you put all that in memory at once. But then the mouse brain has, I think, hundreds of millions of nodes. So basically, you've trained the model over 16 or 32 nodes, and now you're deploying it on a graph that's 180,000 times larger than the graph you learned to execute the algorithm on. And already in this scenario, without any hyperparameter tuning whatsoever, we were able to outperform a previous state-of-the-art baseline by a significant margin, 5 to 6%. Basically, just by putting this extra pre-trained frozen component that updates your embeddings based on the flow algorithm. So you can imagine what would have happened if we actually tried to do some hyperparameter tuning. And I think this kind of ease of how well we got the result was part of the reason why we got the spotlight at iClear. And the dual algorithmic training was actually critical in this case. One thing that's interesting to note here is that not all polynomial time algorithms are equally easy to learn by a GNN, even if they encode exactly the same information. So max flow is actually much harder to learn than min cut for a GNN, because max flow requires you to do for every edge a regression task, and this regression values must satisfy the flow constraints and all other sorts of things. Really tricky to learn. Whereas min cut, you can treat it as a binary classification of each node. Is it in the same cut as the source, right? And this is actually something you can learn with 100% accuracy with a GNN, even out of distribution. But a max flow has some mean squared error that we cannot surpass. But you have to, basically the flow solver needs the reinforcement and the stability from the min cut solver in order to get more stable results. You don't get the good results if you just train on one of them. So hopefully this gives you some intuition behind how we can take these systems, deploy them somewhere else, scale them up, try to solve real world problems that depend on algorithms. I think there's lots of such problems out there and lots of opportunity for impact. But one question that I guess arises from this is, where can we get good processors from in general? And, generally the problem is, how do we know which algorithms to execute in a typical, downstream problem? As you've seen in the DAR example, this is something that requires you to have domain knowledge as well as computer science knowledge, right? You need a domain person to tell you which target algorithm would make sense for the task. And you need a computer science person to build a data set so you can use it to train a model. So there's a big barrier of entry, in my opinion. So we wanted to reduce it and just have a good collection of processors that don't require prior domain knowledge, but are a good basis for learning to do basically everything else. And, we took as inspiration one resource that I think should be familiar to most of you. This textbook over here, which marked half of my computer science education. And even though it has several thousands of pages, it really only has about 90 algorithms, 90 distinct algorithms. And those algorithms are usually the basis of a foundation of a software engineer's career, right? So if you learn those, that can be a pretty solid basis you can then use to mix and match and learn new stuff, right? Now, we have built a benchmark where you learn to execute some algorithms from this book. We did not take every single one of them, so I have to disappoint you. We only took about a third, so 30. That's the reason why it's CLRS-30 and not 90. But if you look at the algorithms we already have in the benchmark, you can see we span basically all of the key skills. So you have a bit of sorting, bit of searching, bit of pathfinding, dynamic programming, string matching. We even have geometric algorithms like convex Hall finding. So you can teach your GNN very easily to execute any of the algorithms inside this collection here. And what's great about it is it's publicly available. So if you're interested in throwing your own model at these kinds of execution tasks for these 30 tasks in any combination you want, there is a GitHub. This GitHub has all the links you need. It's exactly the same code base we use internally at DeepMind for experimentation. There's also a companion paper, which we released at ICML last year. So if you want to get started, a lot of these, especially simpler algorithms, don't even require a GPU. So it's very cool for student projects as well. Now, what's special about our benchmark, and why did it take 2.5 years to build it. It's because we don't just give you inputs and outputs indefinitely for some particular distribution. We expose the entire trajectory of all of these algorithms, and in a way that aligns with parallel computation as much as possible. So for insertion sort, for example, here, we give you every single step of how insertion sort rearranges the green pointers of the list. And it also gives you access to the algorithm's intermediate state. You have a red pointer telling you which element is being sorted into place right now. You have a blue pointer telling you where does that element land in the partially sorted list. All of this is given to you as a direct supervision signal you can learn from in an autoregressive way. And what's really cool about this is that once you specify these variables and then have a data sampler, this uniquely determines basically an infinite data set shape for this task. And the library not only builds the dataset generators for you, it also builds the models encoder and decoder functions because they're automatically specified by the types of the algorithm, and loss functions. So all of this is done by the library for you. You don't have to worry about writing batching code, loss code, generator code. You just have to write your model, your processor network, and just use our default run scripts to do this. So you can think of CLRS really as a dataset and baseline generator rather than a single dataset. And that's what I think makes it very powerful for future research and algorithmic execution. Now, you try to teach a model to execute this kind of computation, and you might then raise the question of what has this model actually learned to do? This is a question we've left unanswered for a long time, and recently we have a paper at this exact same workshop at ICML that tries to study the latent space representations of these models. And in fact, one can learn a great deal about what these GNNs have learned to do by analyzing some low dimensional projections of their node embeddings that they have in the high dimensional space. So in the work of Vladimir Viktor Mirjanic, we have taken the first plunge towards this. And the key idea is we pre-train a GNN to execute something like Bellman-Ford, and then this now learns a sequence of node embeddings as it learns to execute the algorithm. So we study how those embeddings change over execution time in some low dimensional space like PCA. And we study also some nodes and time steps where mispredictions are happening. And it helped us not only analyze what's happening inside these models, but also identify some key issues like loss of resolution and value generalization that are critical when learning to extrapolate, along with proposed fixes, which immediately gave us some improvements on the CLRS benchmark. So let's see some of the things we found. Generally, this paper is a treasure trove of really beautiful looking figures, but there's some nice things and insights in those figures as well. So here you have the PCA for a bunch of random inputs on how the embeddings evolve over time as the executor progresses. So it starts from blue, then it moves to orange and so on. So you can see that the variance inside a single step is much bigger than variance across samples. So clearly it has learned to carefully organize the samples into distinct clusters based on time step. And it converges eventually to a region of the space, which is like an attractor, which corresponds to the termination state of the algorithm. What's very nice is the model has learned to preserve symmetries, even though it learns highly nonlinear functions in general. If we multiply all the weights in our Bellman-Ford problem with a scalar, the shortest path should be still the same, just multiplied by a scalar. So basically you get these nice parallel lines in PCA space, which is also cool. And the execution lines also remain parallel, which is very nice. And lastly, we used some reweighing symmetries like the ones used by Johnson's algorithm to generate lots of different graphs that have exactly the same shortest paths. And we saw that from these 8 prototypical examples, the model learned basically to generate 8 distinct clusters of execution. So it learns to group together models that inputs that will have the same shortest paths in the end, even though they might look very different to each other at the beginning. We can also analyze where does it fail to predict. Is it learning a non-trivial heuristic? And we can see actually it fits the Bellman-Ford algorithm a lot better than, say, a greedy version that just takes the shortest edge out of every node, or some decay or noisy versions of it. And we actually find that it gets the best performance in the attractor node, so the step offset of 0, and it predicts badly the nodes that are furthest away from the source. Basically, this is a sign of value generalization, which is a much trickier problem than size generalization. So if at test time you come across numbers that are much bigger than the numbers you've seen at training time, this numerically really hurts the model. And this is something we need to try to solve in the future. I have a few possible ideas, but they're very preliminary. The second question we can try to ask ourselves is, can we use these trajectories now that we have them? So CLRS exposes very nice trajectories. Can we use them in more interesting ways than just learning to imitate one step at a time? And if you remember previously, this was key to our success, and CLRS-30 supports this step-by-step training out of the box. You don't have to do anything. However, back when we released the CLRS benchmark, there were lots of new architectural tricks that showed that this autoregressive training stopped being necessary, to the extent that you can just learn to predict the output directly from the input and get competitive or even better performance. The paper from Madavi and others has a very nice summary of this result. So what's the most likely culprit? Like, why did we suddenly get much better at doing this without fitting step by step? It's most likely this idea of recall mechanism that was concurrently published at NeurIPS by folks from Maryland, which is a very simple idea. Feed back the input to the processor at every step. Remind it what it's supposed to be solving. So even though the representations might diverge from the true trajectory, you always have your input to ground you back to the original graph that you're trying to solve. And this on its own proved to be more powerful than stepwise supervision. But still, there's lots of useful steps. Can we find a way to make those steps useful again? This is what we tried to answer. And in our ICML paper with Petar Veličković and others, we actually have found such a way. And that is, we stop trying to fit every step one at a time, but we actually make use of algorithmic invariants. See this depth first search example. You explore node 1, then node 2, then node 3, then you backtrack into node 2, and then you explore 4. This next step, going from 2 to 4, would have happened equally even if I added a lot of new nodes and edges into the graph. So everything here, which is in dashed, are new nodes and edges I could have added, and that doesn't change the first 4 steps of this algorithm. It's a bit of an invariant of the algorithm. So can we kind of teach a model to recognize these invariants? It turns out we can, and we do this by using a causal framework. So we split our inputs into what's relevant for the current step and what's irrelevant, and then using a causal terminology, we can do arbitrary interventions on the background, and it doesn't change the input. In the context of bubble sort, for example, you're only ever looking at 2 nodes at a time, the nodes in green. The nodes in gray are irrelevant for the current step. You can do whatever you want to them. It is still going to do the same swap. Yeah. So this is the set of salient inputs are usually much smaller than the graph size. So we can exploit lots of interesting augmentations to perturb these irrelevant inputs at any step of the time. And we can formalize this using a causal diagram. So any interventions on the non-salient nodes shouldn't modify the outcome. And using this, we're actually able to prove that we learned this kind of contrastive objective where we try to push these 2 representations closer together and pull apart representations with any of these other nodes. So it's a simple kind of positive negative sampling you can do. And you can prove that if you optimize such a contrastive objective, if it goes to 0, it's the same as if you learned step-by-step execution, like you will know how to execute every single step. Now, of course, this now means you have a lot more freedom in where your representations go because you're not forcing them to predict every single step, but you can be comfortable knowing that if you optimize such a positive negative loss, you'll still get a good performance. And what we do is we make just 2 augmentations of the input, which produce the same partial trajectory. And then we force the embeddings of those 2 inputs to be the same for the nodes that are relevant. And once we do this, this is our paper published at ICML, we actually massively improve on almost all of the algorithms in CLRS out of distribution. So even on algorithms that we previously really struggled on, we now have performance of about 90% and above, which means that very soon we need a bigger, larger test set. Like this test set is almost solved at this point. And actually, it makes hints, these trajectories, useful again. So if we compare the results of our hint relic method with the previous best method, which doesn't use the stepwise supervision, we outperform it in basically almost all of the cases. Now, the last question I want to talk to you about before concluding this talk is, we've talked so much about learning to capture computation of one algorithm, but I've showed you now a benchmark of 30. And they all have the same graph representation internally. So why stop at 1? Could we actually try to learn all 30 of them? Also, we sort of promised we would do it. Well, not really. We were giving an interview with this journalist in VentureBeat, and he decided to put in the title as journalists do, right? And now we felt we had to deliver on this promise, right? Let's see what we can do. So, arguably CLRS-30 is a way to enable multitask research, and secretly it's why we built it in the first place. So try to have one GNN processor that can execute all of those algorithms together. Can we learn one processor to execute all of them? So what I mean by this is a picture like the following. So I have a shared processor in the middle, and I have these 30 algorithms like sorting, pathfinding, convex hull finding. I embed each one of them with a separate encoder, and I decode all of them with separate decoders. But the central component is shared, and we make it responsible for most of the computation by making all of these guys linear layers, right? So simple linear projections, followed by deep processor, followed by linear projections. And can we just do this in a multitask way using CLRS-30? It's very easy to do in code, but it's not as trivial as just throw a bunch of batches together and see what happens. We quickly ran into NANs doing this, and some previous results like Neural Executor++ even implied this cannot be done if the algorithms are not highly related to each other, like Prim and Dijkstra or something like that. But actually, we realized you can do it. There's just a problem if a task is really unstable, like really noisy gradients or something like that, it messes up the learning for all the other tasks. So we actually started off our effort by trying to improve the single task stability, make the gradients as stable as we possibly can. And we had a short several-month mini strike, trying many ways to do this. And we actually improved our specialist models by quite a bit, because you can see here, in the 3 columns here are our previous state-of-the-art methods on auto-distribution CLRS. You can see only about 50% accuracy across the algorithms on average. But our new model, which incorporates a lot of new tricks like triplet mechanisms, gating, sync-horn operators for sorting, and so on, we're actually able to improve the average performance by about 25% in absolute terms. And if you look at the number of algorithms we can execute better than 90%, better than 80%, better than 60%, those numbers are all very much up on this new architecture. And with that architecture as the base model, we actually were able to do multitask training, which did not break. So here in blue, you have the performance of single task specialist GNNs on each algorithm. And on the orange, that same GNN trained in a multitask regime. So as you can see, there are some tasks where the multitask model is much, much better out of distribution. There are some tasks where it's worse. But if you take the average, which are the 2 bar plots at the far end, you can see they are roughly the same. So basically, we on average have a single generalist model that matches the performance of the 30 specialists. So I would argue that this was successful, and we actually had a lot of ablations to kind of confirm that it was successful. So on these 2 pictures, you have about 3,000 experiments worth of data, where we gradually took out the individual things we added to the model and see how the test performance of the model deteriorates as you remove it one after another. So every single thing we added actually helped significantly to get better generalizing multitask reasoners. And some of the early steps, like basic architectures, are not even in this plot because they result in NANs or infinities or something like that. So this paper got us a spotlight at Learning on Graphs 2022. And if you're interested, you can look it up. There's an archive link over here. But arguably, this might be a first step indication that we have been successful in learning one algorithm to rule them all, whatever that means. But how do we measure success? Let's ask what the public says about our work. Let's look at Reddit, for example. So I went on r/Singularity, which is a very appropriate venue for these sorts of discussions. And I looked at some of the things that posters on r/Singularity wrote about our paper. So first, it's not new. Okay, others tried to solve it, got some success, but our model has a lot more success. Nice. Somebody thinks it's a pretty big deal because as they have training in psychology, it's close to one of our guesses as to how a brain works. I am not a psychologist, so I cannot say this for sure, but it sounds nice. Remember how GPT-3 impresses us with fluent writing, but makes embarrassing blunders in arithmetic, basic logic, multi-step reasoning? This is a way to incorporate algorithmic reasoning into such models to reduce such blunders. I tend to agree. And lastly, my personal favorite, if you think of artificial general intelligence as a vehicle, Gato, the multitask model from DeepMind, can be seen as the front seat. Maybe our paper acts as the side mirrors. They're all important parts of the final car, some of them arguably more important than others. And if our research ends up being just the side mirrors, I'm still happy with that. So that was basically the last remark I wanted to say. Before opening the floor to questions and discussions, I want to just leave you with a few pointers. If anything I told you today is interesting and you want to learn more. So if you want to learn more about algorithmic reasoning in general, with lots of new references, code examples, collabs, and whatever, we have a 3-hour-long tutorial that we gave at Log. And on this website, algo-reasoning.github.io, you can find all of those resources nicely arranged together. And if you come from combinatorial optimization, which I believe many of you have, after a 3-year wait, I think we have been able to finally publish this 61-page survey at JMLR, which is joint work with actually many of the people affiliated with this group. And specifically, if you look at section 3.3 of that paper, it talks a lot about the kinds of things we discussed today, algorithmic reasoning, but it also talks in a lot more broad fashion, how can you use graph neural networks to help you solve not only polynomial time problems in execution, but also even NP-hard problems. So that's the last slide. Listening, and thanks again for the invitation. Happy to take questions. You have my email here as well if you want to reach out afterwards. I need to say at the end, it really takes a village to cultivate this collection of research from the ground up, and very soon I'm going to run out of a slide listing just all the people who have collaborated on all these papers with me. So thank you all so much, and I'm happy to take questions.